All right, hello everybody. This lesson is going over Unit 1, Lesson 2 in the AP Chemistry curriculum. We're going to be talking about mass spectroscopy of different elements today, and the learning objective is to explain the quantitative relationship between the mass spectrum of an element and the masses of that element's isotopes. So a mass spectrum is going to show the different isotopes of an element and how common each one is. And by using both the mass of each isotope and how often it occurs, scientists are going to be able to calculate the element's average atomic mass as a weighted average. So isotopes are defined as having the same number of protons and electrons, but a different number of neutrons. This discovery of isotopes updated Dalton's idea that all atoms of an element are identical, because now we know that atoms of the same element can vary in mass, but their chemical behavior is going to stay the same because they have the same number of electrons. So just remember, when we're talking about isotopes, electrons are going to control the chemical properties. So since all the isotopes have the same number of electrons, they're going to have the same reactivity in different chemical reactions. So consider the following pairs. Does either represent a pair of isotopes? So the first two is potassium and argon. We see that they have the exact same mass number, which is the number on top, the number of protons and neutrons, but they have a different number of protons, which is why they're different elements. Now remember in the last slide we talked about isotopes having the same number of protons and electrons, but a different number of neutrons. Here we have two elements with a different number of protons, so they are not isotopes. Now on the bottom we have strontium-90 and strontium-94. Both are strontium, which means they have the same number of protons. They have the same number of electrons because there is no charge on these elements. And then they have a different number of neutrons because their mass number is different. So strontium-90 and strontium-94 would be considered isotopes. Now remember from your past chemistry knowledge, the number on the top is the mass number, which is the protons plus the neutrons, and the bottom number is the atomic number, which is just the number of protons. So if you wanted to figure out the number of neutrons in each isotope, you would just take the top number and subtract the bottom number. So strontium-90 has 52 neutrons and strontium-94 has 56 neutrons. Right, so recapping what I said on the previous slide, over here on the right is what's called isotope notation or an isotope symbol. So the X is going to represent the symbol that you can find in the periodic table. So for example, lithium, its symbol would be Li. A would represent the mass number, which is the number of protons and neutrons in that isotope. And then Z would be your atomic number, which is the number of protons. And remember that the number of protons is literally the identity of the element. So if you change the number of protons, then you are changing the element completely. So looking at the lithium example to the left, we have three naturally occurring isotopes of lithium. We have lithium-6, lithium-7, and lithium-8. Notice that the atomic number, the number of protons, is the same for lithium because if it didn't have 3 protons, it's no longer lithium. So isotopes are always going to have the same number of protons, but what's changing in this isotope notation is the top number, which is the mass number. And the reason it's changing is because of the number of neutrons. So lithium-6 has 3 neutrons, lithium-7 has 4 neutrons, and lithium-8 has 5 neutrons. Boron shows up on our periodic table as 10.81 AMU or grams per mole. If there are two naturally occurring isotopes of boron, boron-10 and boron-11, what can you conclude about each isotope? Now remember, the elements on the periodic table, when you look at their molar mass, that's going to be a weighted average of all of the isotopes. So if we know we have boron-10, which has a mass number of 10, and we have boron-11, which is a mass number of 11, we can look at this weighted average and see that it's closer to 11 than it is 10. Which means there are more of the boron-11 isotope than there are the boron-10 isotope. Neon has 3 isotopes of masses 22, 21, and 20 AMU. If the isotopes have the abundance 8.01%, 1.99%, and 90%, what is the average atomic mass of neon atoms? So when we are trying to find the weighted average of something, we're going to take the mass and multiply it by its relative percent, and then we're going to add all of those up together to get our total weighted average. So our first isotope has a mass number of 22, and its relative percent is going to be 0.0801. Then we're going to add that with our second isotope, which has a mass number of 21, and its relative percent is going to be 0.0199. And then our final isotope of 20, we are going to multiply it by its relative percent, which is 0.9. So when we calculate that, we end up getting a weighted atomic average of 20.1801. Now this should make sense to us because we have 3 isotopes, 22, 21, and 20, which means our average atomic mass has to be between 20 and 22. And since our isotope of a mass of 20 is 90% abundant, we can assume that the average atomic mass is going to be much closer to 20 than it is to 22. So an average atomic mass of 20.1801 makes a lot of sense. And then this figure on the right here is just another example if you want to quickly run through it before we move on. A naturally occurring sample of an element consists of 2 isotopes, one with a mass of 85 AMU and one with a mass of 87 AMU. The abundance of these isotopes is 71% and 29% respectively. Calculate the average atomic mass of an atom of the element and identify the element. So we are looking for the average atomic mass. So we're going to take our mass of 85, multiply it by its relative percent, which would be 0.71. And then we're going to add it with our other isotope, which has a mass of 87 and a relative percent of 0.29. And that's going to give us a weighted atomic average of 85.58 AMU. Now again, I want to make sure you see the relationship so that when you have quick multiple choice questions on this, sometimes you don't have to do the math. You can just do it based off reasoning. So we have 2 isotopes with a mass of 85 to 87, which means its average atomic mass has to be between 85 and 87. Now, since the isotope with the mass of 85 is much more abundant, we're going to assume that the average atomic mass is going to be much closer to 85 than it is to 87, which makes sense when we did the math. We got 85.58, which is much closer to 85 than it is to 87. Now at this point, it says identify the element. So you're going to go to your periodic table and find the element that has the closest atomic mass to what we just found. And if you look on your periodic table, you will see an element that has a molar mass of 85.47, which is the closest, so the element will be rubidium. The next question says, 2 isotopes of gallium occur in the respective percentages of 62.1 and 37.9%. Calculate the average atomic mass of gallium atoms. So at this point, I want you to pause the video and try this one on your own, and then I'm going to pull up the key so you can check your work. Okay, so I hope between the start of this video and now, you kind of ask yourself, well, how do they know how abundant some of the isotopes are? Well, they know it through something called a mass spectrometer. So with a mass spectrometer, essentially what it does is it takes the sample of atoms and it ionizes those atoms into positive ions. And those ions are shot through this spectrometer and put through a magnet. And when the ions are put through that magnet, they're going to deflect. And when they're deflected, some are going to deflect more than others based off their size. And as we know from the previous slides, the difference between these isotopes are their mass because they have a different number of neutrons. So since they all have the same charge, the only thing that would make one atom deflect more or less than the other is going to be the mass. So the lighter ions are going to deflect more than the heavier ones. And we cannot see this happening with the human eye, but the mass spectrometer is going to put out data that's going to tell us how abundant each isotope will be. So this is something called a mass spectrum, which is the data that we get from a mass spectrometer. So here we see a mass spectrum of chlorine, and you can see that there are two isotopes. We have isotope with a mass of 35 and isotope with a mass of 37. And then on the y-axis, we have our percent abundance. So we can see that our chlorine 35 has a percent abundance of about 76, and our chlorine 37 has a percent abundance of about 24%. So the first question on this slide says, which isotope is more abundant? So we know percent abundance, the higher one is chlorine 35. So chlorine 35 would be the answer to that question. Then it says, from this graph, show calculations for obtaining the average atomic mass. So we've done this a few times already, so I'm just going to go through it one more time. So we have our first isotope with a mass number of 35 and a relative abundance of 0.76, added with our other isotope with a mass number of 37 times its percent or relative abundance, which is 0.24. And when we calculate that, we get an average atomic mass of 35.48, which is very close to what you were given on your periodic table of 35.45. In this graph, which isotope is the most abundant? So remember, relative abundance is going to be on the y-axis, so the higher the bar, the more abundant it is. So our most abundant isotope is going to be zirconium-90. Next question says, looking at this table, do you think the molar mass of zirconium is closer to 96 or closer to 90? So again, when we're looking and interpreting these graphs, we can see that we have isotopes from 90 to 96. So we know our average atomic mass is going to be somewhere between 90 and 96. It can't be less than that range. It can't be more than that range. Now, as we can see, our most abundant isotope of zirconium is 90. Which means our average atomic mass is going to heavily stay on the lower end of that range. So we can guess that it's going to be closer to 90 than it is to 96. And then the last question says, how would you solve for average atomic mass? And that's by multiplying each of the masses by its relative abundance and then adding them all together like we've done. So go ahead and pause, and I would try to do this one in your calculator without writing it out, and then I will show you the work in a second. And this is my work for this question. Little side note here, if you're given a question like this, let's say on a free response question on the AP Chem test, there will definitely be a range because some of these bar graphs could be misinterpreted. So example, if you said 51 for zirconium 90, and then you had 17 for zirconium 92 and 94, and you just kind of were a little bit off from what I assumed on this graph, that's okay, as long as you're in a certain range for the AP chemistry test. All right, so for this example, we are given a mass spec on the left, and we are asked to figure out which element it is. So the first thing I want you to note is the different mass numbers in the isotopes given. So we have a mass number of 39, 40, and 41, which is going to tell us that the average atomic mass must be between 39 and 41. It cannot be lower than 39. It cannot be greater than 41, which means if we're looking at our periodic table, we're really left with three potential options. And those are argon, potassium, and calcium. Now looking at our mass spec over here on the left, we can see that the element isotope with a mass number of 39 is much more abundant than the other two, which means we know its average atomic mass is going to be really close to 39. So that's going to tell us it's going to be potassium. So for the first part of this question, it says identify the isotopes and their abundant. We have potassium 39, we have potassium 40, and we have potassium 41. It looks as if potassium 39 is right about 92% abundant. And potassium 40 looks about 2% abundant, and potassium 41 looks about 6% abundant. Then it says to estimate the average atomic mass. Again, looking at the periodic table and looking at what we have here, I would probably estimate the average atomic mass close to what it was on the periodic table at 39.1. And then the last question is saying, if you were to calculate the average atomic mass from this mass spec that we were given, how would that compare to the one given to you in your periodic table? So let's go ahead and solve for the average atomic mass using this data here. And when we do that, we get a weighted atomic mass of 39.14, which shows that the calculated version is slightly higher than the version on our periodic table. All right, so we have another practice question on calculating the average atomic mass. So I'll go ahead and pause this video, try it, and then replay it to see the answer. And when you do that, you should get 24.32, which again goes with what we see on the mass spec. Since we know the number has to be between 24 and 26, and magnesium 24 is so much more abundant, we can assume that the average atomic mass is going to be much closer to 24 than it is to 26. And then how many neutrons does each isotope have? Just remember, if you ever have a question like this, you're just taking the mass number and subtracting the number of protons. So since magnesium has 12 protons, which is its atomic number, we can take our mass number, subtract 12, and that's going to give us our number of neutrons. So magnesium 24 will have 12 neutrons, magnesium 25 will have 13 neutrons, and magnesium 26 will have 14 neutrons. Next, I want you to just look at this mass spec and tell me what element it is. If you're paying attention, you'll know that it's the exact same mass spec as the previous example, which means this is magnesium. But if you did not know that, you can look again. We know our average atomic mass is going to be somewhere between 24 and 26. We know it's going to be much closer to 24. So if you look at your periodic table, magnesium has an average atomic mass of 24.3, which checks out with this mass spec. All right, so for this one, I want you to pause the video and go ahead and try to guess which one of the elements on the periodic table have this mass spec. So looking at this mass spec, I know that the range is going to be between 92 and 100. So the first thing I'm going to do is look at my periodic table and see which elements have an average atomic mass between 92 and 100. And if I look at my periodic table and I look at element number 41 and 42, those are the only two that it could be. And that's NB with a molar mass of 92.91 and MO with a molar mass of 95.95. Now, if those are my only two options, I can see that the isotope 92 is not the most abundant in the sample. So NB would not make sense to choose as my option. So my answer choice would be MO. And then just so you can practice sketching one of the graphs, I would like you to sketch the mass spectrum that you might expect to observe if bromine were passed through a mass spectrometer. The two isotopes of bromine are bromine 79 and bromine 81, and they are known to exist in an approximately 1-to-1 ratio. So go ahead and pause the video and sketch out that mass spec and press play when you're ready to see the key. So the first thing I would do is go ahead and write out the X and Y axis and label them and put on their data points. So 4% abundance, I know it's going to be about 50-50 since it's a 1-to-1 ratio. So I did my tallies up to 60 by tens. And then on the x-axis, I know I'm going to have two isotopes of 79 and 81. So I just did the range from 79 to 81. So now to actually mark my two isotopes, I know they're both going to go up to 50. It's going to be a pretty straightforward mass spec. And I have seen FRQs ask for something very similar, so just keep this in mind. All right, and for the last slide of this lesson, I just want you to pause and try to do these two problems. If you press play and you got the right answers, I love that for you. I'm so glad you learned something. If not, please come see me or ask me questions, and I'm happy to help. Have a great day.